Idea Statica Concrete. Myself, Jarajan P. This is tutorial number 3 and it will provide how to perform the design of a T-beam using the Idea Statica Concrete module beam. So let us first go through the problem statement. So as shown in the figure, a slab is cast integrally with a series of beams as shown here, and essentially it's a one-way slab as shown here. So we are going to proceed with the design of an intermediate beam B1. So in this case, we know that as the beam B1 bends, the top fiber will always be in compression, and accordingly, a certain width of the slab will act integrally along with the beam B1, forming a T-beam action. So the typical T-beam that is considered for the analysis and design is shown here. It has a span of 6 meters. It is essentially subjected to uniformly distributed loads. And under the loads, as usual, we have two actions. One is a permanent action denoted by G, and that is equal to 30 kN per meter. Please remember that sulfate is already included in this G value, and therefore accordingly it will not be separately considered. Now then we have the variable action Q, that's a 15 kN per meter. The exposure loss will be considered as carbonation XC1 category. Now regarding the code, we shall use EZ2 for the design verifications in both ULS and SLS. And regarding the material, we will use concrete of grade C2530 and reinforcement of grade 500 and class B. And for the combinations, the ULS verifications will be done as per the combinations taken from 6 ton of EN1990. And for the SLS, we shall use three combinations, popularly known as the characteristic combination, frequent combination, and quasi-permanent combination. And these shall be as per equation 614b, 615b, and 616b of EZ0. Now the verifications will be performed both for the ULS and SLS. Under ULS, we shall perform three verifications, namely the check on the design moment of resistance, the shear capacity of the given section, and finally an interaction of the moment and shear. And regarding the serviceability, we shall perform the stress limitation in concrete and reinforcement using both the characteristic and quasi combination, the crack control using the quasi combinations, and deflection control using a characteristic combination. So let us first see the details of the cross sections before going into the Idea Statica program. So in this case, you can say that the 6 meter beam, it is simplified into two reinforcement zones. One zone of length 1.5, then you have got a central zone of length 3.00, and the reinforcement details are characterized by two cross sections, section AA and section BB. And as you can see that the overall dimensions are given here. The depth of the T section is 500, its width is 250 mm, and the thickness of the slab is 125 mm. And as you can see that both AA and BB are of the same cross section, and their difference is only in the reinforcement details. While in section AA, where we have got a lesser moment, the bottom reinforcement consists of only 325, whereas at BB, where we expect a larger moment, we are, in addition to 325, we have got an additional 220 dia bars. And for section AA, we have got the two-legged 10 dia straps at 150 mm, and at BB, we have the same two-legged 10 dia straps but at a larger spacing, 250 mm. So let us proceed to now Idea Statica beam module. Okay, fine. So we are now in Idea Statica beam module. So as usual, please verify the units, whether all the system of units are accessible to you. Looking into the main material and also the results. If you want to make any changes, you can change it. Here we are accept the default units. Okay, and now we can also look into the preferences. And in the preferences, okay, you can select the language. You can select the unit system. You select a metric system of units. That's okay for us. So we can straight away proceed for starting a new project. As I already mentioned, we are considering a cast sensitive concrete beam. Is a reinforced concrete beam, and we are considering basically is a single span beam. And as discussed in the previous tutorials, the beam alignment is set as top surface and support position as bottom surface. Press the next level. So we are going to consider a single straight beam that is not in the vertical plane, and we are going to consider a simple span beam that has only two supports at the ends. So let us provide the length of the beam as 6 meters. Again, press next. Now the design code will be easy to, and the national annex will be EN only. Design working life will be chosen as 50 years. Now let us proceed for the cross section. So let us see that whether the cross sections are as per our requirement. So press a T shape. Okay. So as you can see that yes, it provides you all the parameters. So H is nothing but it's the overall depth. That is we have to change it as 500 mm. The overall depth is 500 mm. And then we have B. What is B? B is the effective width of the flange. Please remember, effective width B has to be calculated strictly as per the code requirements based on the spacing of the beams and also based on the distance between the points of counterflexure. In this case, we assume it as directly the effective length as 600 mm. Okay, and then the width of the web we consider as 250 mm. Okay, so BW, please remember that all the parameters are given here, so that you will be able to easily identify what this symbol stands for. HF is the thickness of the slab. This will consider as 125 mm. Okay, so remember 500 is the overall depth, B is the effective length of the compression flange, that is 600, and BW is the what we call as the width of the web, that is 250 mm, and the thickness of the slab, that is equal to 125 mm. So now the concrete C2530 is acceptable to us, so we can just press OK. So this means that we have created the what we call as the cross sections properly. Now let us start applying the loads, and as already discussed, the loads, let us just quickly go through the loads. It is a 30 and 15. Okay, so let us just apply it over here. This is a G action. It is a minus 30 kilometer meter, and the variable action will be 15 kilometer meter. So finish. So this means that now the idea Statica will proceed with the analysis of the beam with all the default parameters. Now, before seeing the results, as already explained in the previous tutorials, please go through all these, the ribbon items and ensure that the data is acceptable. For example, you can say that yes, we are using a national annex EN, and the design code will be EN, and the reinforced concrete beam, all those things. And you can go to the cross sections. You can just see all the cross section dimensions, whether it is acceptable to you, and you can also see the properties of this cross section by pressing into the characteristics of the section, which will provide you the moment of inertia, location of the center, etc. That is anyway not will not be shown here. So now coming to the materials, you can say that yes, it consists of SE2530 concrete. Fine. Now coming to the geometry, you can say that yes, we have basically is a 6 meter visibly supported beam. Okay, and the supports, we have the two supports over here. Obviously right now you don't have the supports marked here. Just push the node numbers, you get 1 and 2 node numbers. As you can see that the node number 1, it is pinned, that is the restraint in x and z directions, and as far as 2 is concerned, it is on rollers. Accordingly only the vertical displacement is restrained. So now coming to the loads, that is very important for us. As you can say here that we have SW self-weight, the permanent load G, and the variable load Q. Now as already explained earlier, the value of the sulfate is already assembled with the G. So accordingly what we can do is we can just delete this SW. Okay, so you can just remove it from this load group. So this means that we have only two basic actions, G and Q, and as you can see that this is minus 30 and the Q, it is equal to minus 50. Okay, so that is all regarding the load cases, and we don't have any kind of the point forces or any other uniform loads to feed here. If you have got some additional concentrated load, you can feed into the system using the point forces. If you go into the combination, you can see that yes, we have basically one combination for the ULS and three combinations for the SLS as already explained. And here, the idea Statica beam module provides you the facility either to choose equation 6 ton AB or directly 6 ton. I will use code 6 ton, equation 6 ton of EZ0 for the formulation of the load combination corresponding to the ultimate limit state, and all the SLS C, F, and Q, which represents the characteristic frequent and the quasi-permanent combinations, are given here. So it means that the load combinations are okay for us. So now we can proceed for the calculating, so that we will be able to see the reactions, we'll be able to see the moments, etc. So let's just start seeing the reactions first. So here we'll be able to see the reactions. As you can see that, for example, ULS we have got 189 kilonewton, and you can also see for the individual cases for G, we find that there is a load of say 90 kilonewton. This is acceptable because we applied a load of a 30, so 30 into 3 should be 90 kilonewton, and my Q must be just half of it, that is a 45. It's okay for us. So let us quickly proceed for the internal force. And in the internal force, we need to see basically the shear force. So you can check the shear force over here, Bz. So you can just fit this. So you can see that as usual for the ULS, suppose that you are interested in the ultimate limit state, you can see that for the two limit states, it has provided the values. So if you want to read it, you can just you can see that it is the value is say 189 kilonewton is the maximum shear force. Similarly, we can also see the so-called the variation of the minimum diagram. You can see that the ultimate corresponding to the ULS of the maximum minimum did not reach 283.5 kilonewton meter, and all those values are also indicated in the table below. And below you can also find, that the critical combinations, if for example ULSF2 is 1.35 G plus 1.5 Q. Okay, fine. So this means that yes, we are comfortable with all the loadings, all the load combinations, and all the obtained internal forces in terms of the shears and the bendings. We are ready to proceed with the concrete design. Okay, so let us start providing all the input to the program regarding the concrete design 1D. So press the data. So here, as you can see that yes, it will ask what are the verifications and checks you want to carry out. You want to carry out the capacity verification, shear interaction, stress limitation, crack width, detailing, okay, and the deflections. I don't want the detailed calculations. I'm happy if it compares the L by D limits obtained from equation 742 of EC2. So I'll select that. Then I don't want any redistribution of the moments, no reduction of the moments, but I will go ahead with the reduction of the shear force. Okay, so then what are the other checks? Lateral stability also I would like to check. And okay, fine. Here is another important input that need to be provided. That means the exposure class. And here we assume that the carbonation of XC1, okay, and we assume that for the site there is nothing like a chloride attack either from the direct or from the sea. So there is no risk either for the chlorides or from the freeze or chemical attack. So exposure class essentially consists of XC1 type only. So this means that our data is okay. Now let's go ahead with another important item, that is prescribing the reinforcement. So as you can see that Idea Statica provides two cross sections and we need to provide the details. So suppose I want to change the reinforcement details for AA, just double click it. It gives you a template. So here you can say that 3-4 templates are there, of which I will be selecting the third one, because the third one will permit me to provide the multiple layers of the reinforcement. So I'll just double click it. So here let us start feeding it. This is section AA. So in the upper layer I'll be using the 416. Okay, it's the upper layer bar, and the second layer I don't have any bar, and the lower layer obviously will have the 325, right? The lower layer, that is the L1, IL1, and IL2 is a section AA1. I don't have any bar, and select the proper grade. Okay, and then coming to the edge bars, I would like to provide one number of edge bar, that is edge bar, I mean the bars that is provided along the web. So and the diameter will be fixed at 10. And coming to the struts, we'll use say 10 mm dia struts, and we shall use a strut spacing of 0.15. So I will select it as 0.15. So this is okay for me. So you can find that yes, the details are provided over here. So essentially it consists of 3 bars at the bottom, 4 bars at the top, and you will find that there are 2 shear legs as shown over here, right? So this is acceptable to us. So you can press OK here, And here again you will find that the areas also listed over here. On the top we have got 416 giving to 804, and the bottom we have got 325 bars providing an area of 1473, etc. So this is okay for us as far as the AA is concerned. So you can say that AA details are directly provided over here. 416 top, 2 turn sideways, 325 bottom, and turn diagonal 2 lakh at 150 mm, right? So now we can in a similar way proceed for section BB. Let me just, okay, this is my B, so let's just press this part. So here as you can see that we'll be using the third one, and here it remains 416 is okay, and the lower layer we would like to keep the lower layer at 325. We would like to have the second lower layer, we want to introduce 220 bars, right? 220 bars, and it's okay. All these are acceptable, and the strip spacing I want to increase it. So rather than 150, let me just use it as a 250. So I'll use this at 0.25. So this is okay. So you can say that yes, the reinforcement is already provided over here for the section BB. So this is okay for us. So you can say that we have provided into the system both section AA and section BB. Now redistribute. Now coming to the lateral stability. So here for the lateral stability, you can feed B. What is B? Let us see. The width of the compression flange. We know that the width of the compression flange for this problem is 0.6. Okay. So what is the H? Let's see what is this H. It is the total depth of the beam. Okay. Total depth of the beam. And we know that the total depth that we provided it is the 0.5 meters. Okay. And L0T. This is basically is for the lateral torsion buckling. And this is the distance. We know that it is the total length for the span of the beam, 6 meters. So you can see that it automatically calculates right now itself and see that the static is okay. You can see that the two checks are being performed, one based on the L by B criteria. The limit is 53.13 and the calculated one is 10 is acceptable to us. And then there is one more criteria, that is the H by B, that is the aspect ratio, the cross section, that is 0.83. The limit is 2.5. That's why it says that as far as the lateral stability is concerned, it is acceptable. These are nothing but the code verifications in order to see that yes, the cross sections will not buckle or it will not undergo some second order failures before it reaches its capacity. Okay, so that means that's okay, means that now we are ready to go for the calculation. But before going into the calculation, as I already told you, we need to check into the code parameters. This is a very important part of the calculations. If some of the default parameters of the codes are not acceptable, you have to change it. For example, in this case in chapter 6, you will notice that they have provided theta as 45 degrees, but this provides very overly conservative strip reinforcement. If you assume say theta is equal to 45 degrees, and we need to arrive at an optimum value of theta by equating the compression capacity of the diagonals of the concrete with the capacity of the shear reinforcement. In this case, rather than 25, I would like to provide a value of say 25 degrees. So this is okay for me. So this means that we are ready to go for the calculations. So, so you can say that yes, it is providing all the analysis. So yes, a summary of the calculation is as you can see that it is directly provided here, which indicates that yes, the section that we have provided, it passes all the checks. In capacity, it has got 74.1 percentage, utilization, shear 57.3, interaction 92.2, and stress limitation 91.7, crack width 54.9. So in summary, you can say that yes, your cross section has passed all the verifications or the checks required, and you need to also see the results. You need to study the results properly to see that yes. So you can see that on the top it provides you a failure utility ratio. You can see that the utility ratio is 92.2, whether it is for the zone it is 92.2 zone A, and for zone B you can see that yes, it is also almost the same, that is a 92% something like that. So you can quickly check into the various sections, that's the various zones AA and C, AA and BB. For example, here you will find that as far as section AA is concerned, the cross section is governed by the interaction between the moment and the shear, and the utility ratio is 92.2. Whereas you can see that as far as the section BB is concerned, you know that the is a capacity is governed by the serviceability criteria, that is a stress limitation, that is a 91.7, that is okay. And you can see the details of this summary below. For example, you can see that for the section AA, what we have seen is that the criticality comes from the interaction. So go over AA. Let us see the interaction where it is. So just a minute. Yes, here it is the interaction. You can also see which is the combination that is governing the interaction. Is the ultimate limit state combination number 2 and 92.2. The detail is given over here. And as already described in the previous tutorials, please also go through the non-conformities. If some of the non-conformities are acceptable, keep them. If it is not acceptable, please take the appropriate correction. Okay. And similarly, it is also provided you the section check details for the zone BB. And for the zone BB, here it is given first of all a summary. That is, it is a stress limitation as per the quasi-permanent combination at the serviceability that governs the the check for section zone BB, and we find that the value is 91.7. So you can also see the various utility ratios regarding the shear interaction, stress, etc. Everything. So this is how it is important that you go through all these calculations, right? Ensure that yes, this matches with your hand calculations. So you need to have some a good idea of an approximate calculation, how to perform the approximate calculation, so that you know that we did not commit any mistakes in the parameters, because the code parameters are very important thing, right? So for example, in this case, if you are interested in so the overall check, you can press over here. You can see that yes, the utility of the section is displayed over here. On the other hand, suppose you are interested in the interaction diagrams, you can press the interaction diagrams. Okay, so you can just I can keep this a little bit down. So you'll find that yes, it has provided for solve AA the interaction diagram, right? So let me just zoom this. So we find that yes, it has got okay, all the points that is identified by these combinations 1 to 4, these are all inside this interaction diagram. Okay, fine. So similarly, you can also go with the section BB also. Obviously, for section BB, we arrive at different capacities. So all the points corresponding to the various ULS, these are plotted inside this NM envelope. We find that all these points are very much inside, so that is acceptable to us. Okay, and here idea statica beam module also provides you a facility to import this reinforcement zone uh, into the other module of this idea statica known as RCS. That's a reinforcement calculation module. So that you can import using, there is a facility known as a detailed calculation, detailed check of the reinforced. Let me just tell you one very important thing. Whatever is given in the beam program, that is good enough for you. But on the other hand, if you are interested in having some kind of a very good, a little bit better visual experience, you can go over this, just press this detailed button. You'll find that you will be automatically taken from the module beam to some other module. So here you will find that yes, the module is known as RCS. So this is again a separate module, as it means that, which means that the different modules of the idea statica concrete can be interconnected to each other. So here again, if you want to do the calculations, right? So right now you don't have any result. So here, so you can just press the calculate button, and you'll find that yes, it is automatically be populated, and you find that as usual all the results are green. And for example, suppose we are interested in the results, you can go over to the results, right? And in the results also, you'll find that there are many items as usual. The capacity, okay, here you'll find that the overall check is already provided. You will find that yes, this NM diagram is far better compared to the earlier one. Here you will find that yes, the capacities are being in tension is 165.8. It is marked over here. So if I zoom it, in the NM diagram, you'll find that with the tension, it has got a capacity of 165.8 with compression to 99.8. And we find that all the points for the zone AA, so here is zone AA, that is well within the limits, right? So you can also go for the shear checks, right? And it will show you what is the cross section that is used for the shear verification, etc. Then the interaction checks, it provides you, and look here, this is what I tell you by the visualization experience. This also provides you, for example, for the interaction check, okay, what are the maximum strains? This is the strain diagram, okay, and you know that it is on the top, it's a compression strain, which is of the order of 3.7 into 10 raised to minus 4, and below you'll find that the concrete, the tensile strain is of the order of 9.5 into 10 raised to minus 4, and here is indicated at 0.2. This is the strain. Okay, this is the strain in the bars, and here is again shown the stress distribution, stress diagram. We find that we have a 4.8 kilonewton, 4.8 MPa as a concrete stress, and here the maximum stress in steel is 203.7. Why is the stresses either in 2D or 3D? If you want to see the stresses in 3D, you just press this button. You will find that yes, all the stresses are indicated in the 3D configuration. Okay, so for any what I say that for any zone, whether it is A or BB or for any combination, you can just go on seeing the visualization of the results. You can also see the crack width, all those things. So this is what I mean by the visualization experience. You can just import it, and I feel that for a complex geometry, RCS will be of a really use for us. Otherwise, the beam program module must be good enough for us. So let's just close this. So as usual, what you can do is that you can also go for the results. So suppose that you are interested in a detailed output, you can press the detailed button. As you can see that the idea Statica is writing in the report. So it provides you all the things, for example, the section properties, it provides you all the loading diagrams, it provides you the internal bending diagram, deflection, everything. It provides you the detailed checks associated with the various parts AA and BB. It also provides you what we call as the overall check of section AA and BB. It also provides you the NM diagrams, right? So these are the things that we know, and it also provides you the what we call as the section details. It gives you the total quantity of the reinforcement, right? It will also provide you what's the okay, what's the property of the steel used, etc. So these are the checks, and ensure that all these results have to be verified by approximate hand calculations. You need to have with you the approximate hand calculations, whether it's a very complicated geometry or whether it's a simple geometry. Okay, so I think that that's okay, and I'm very sure that in the coming weeks we'll be able to discuss very interesting problems for like example the corbels, and also like very specialized structures with the horse, etc. So till then, bye.